Imagine for a moment standing on the surface of Mars. The dust beneath your boots glows rust red in the thin afternoon light. Above you, a sky the color of faded butterscotch stretches to a horizon that curves just slightly more sharply than Earth's. In the distance, rising from the ancient plains, gleams a city. Domes of transparent alloy catch the sunlight. Gardens spiral upward inside pressurized towers. People move through corridors carved into bedrock, living, working, raising children beneath alien stars. It is humanity's oldest dream made manifest. A second world. A backup civilization. The promise that we are not forever bound to a single fragile sphere spinning in the cosmic dark. This vision has been painted for us in vivid detail. By engineers, by entrepreneurs, by space agencies speaking with confident timelines. Mars by 2030. 1 million people by 2050. Self-sustaining cities, terraformed atmospheres. A new branch of human civilization unfolding beneath Olympus Mons. The rhetoric is compelling, the imagery breathtaking, and the dream itself. It stirs something deep within us, the ancient impulse to explore, to reach beyond, to plant our flag on distant shores and declare that we belong there too. But tonight, we are going to do something quietly radical. We are going to look beneath the shimmer of that dream, not to crush it, but to understand it, to examine the science that rarely makes it into promotional videos or congressional testimonies, the biology, the physics, the economics, and the psychology that together form an intricate web of challenges far more daunting than the distance itself. Because Mars is not simply far away, it is fundamentally, profoundly alien in ways that matter deeply to creatures built from billions of years of evolution beneath an Earth sky. The question we will explore together is not whether we should dream of Mars. Dreams are essential. They are the compass that guides human progress. The question is whether building a city there, a true, permanent, self-sustaining human settlement, is actually possible. Not in the hopeful language of visionaries, but in the unforgiving mathematics of radiation exposure, bone density loss, atmospheric chemistry, and resource scarcity. What happens when optimism meets thermodynamics? When ambition collides with the relentless demands of human biology? We will journey through obstacles that exist in shadows, invisible radiation that tears through cells, gravity so weak it dissolves our skeletons month by month, an atmosphere thinner than Earth's stratosphere, mostly carbon dioxide, offering neither breath nor protection, psychological abysses that open in minds isolated beyond rescue, medical emergencies where the nearest surgeon is 7 months away, and economic realities so staggering they dwarf the cost of any project humanity has ever attempted. This is not a dismissal. It is an examination, a careful, thoughtful walk through the landscape of what we know, what we suspect, and what remains hauntingly uncertain. Because the truth is, we do not yet know if Mars colonization is impossible, but we do know it is nothing, absolutely nothing, like the glossy renderings suggest. The gap between vision and reality is not measured in years or budgets. It is measured in fundamental questions about what human bodies can endure, what human minds can withstand, and what human societies can afford to sustain across a gulf of space that remains, despite all our technology, almost incomprehensibly vast. Tonight, we will drift through these questions with honesty and wonder. We will honor the dream while respecting the science. We will look at what could go wrong, what has been overlooked, and what alternatives might actually exist if we are willing to think beyond the singular vision of domed cities and red dust streets. If you are settling in for this journey, If you feel the pull of both the dream and the truth, take a moment now to tell us where you are watching from and what time it is in your part of the world. Are you watching as dawn breaks over your city, as night deepens and stars emerge? Wherever you are part of this exploration. Your curiosity matters. Your questions matter. Now, let us begin, not with answers, but with the first and most invisible threat, the silent, relentless tide of radiation that bathes Mars every moment of every day, waiting patiently for human cells to arrive. As we turn our gaze from the outer planets back toward Mars, we must confront a truth that exists beyond the romance of exploration. Mars is not merely distant or cold, it is bathed in radiation that would fundamentally alter human biology. This is not the gentle warmth of sunlight filtering through atmosphere. This is something far more insidious, invisible, and relentless. Earth exists within a protective embrace. Our planet's molten iron core generates a magnetic field that stretches thousands of miles into space, deflecting charged particles from the sun like an invisible shield. Our thick atmosphere absorbs and scatters the remainder. Together, these two guardians ensure that standing beneath an open sky is not just safe, but sustaining. Mars possesses neither of these protections. Billions of years ago, Mars had a global magnetic field of its own. But as its core cooled and solidified, that field collapsed. What remains today are scattered patches of magnetism in ancient crustal rocks, geological fossils of a time when Mars might have been safer. Without this planetary shield, the Martian surface lies exposed to the full fury of space radiation. Its atmosphere, less than 1% the thickness of Earth's, offers virtually no barrier. To stand on Mars is to stand naked before the cosmos. The numbers are sobering. On Earth, we receive approximately 0.3 to 0.6 millisieverts of radiation per year from cosmic sources. Astronauts aboard the International Space Station, protected by Earth's magnetic field even at their altitude, receive roughly 144 millisieverts annually. On the surface of Mars, current estimates suggest exposure levels of 250 millisieverts per year or higher. During solar particle events, violent eruptions from the sun, those levels can spike dramatically within hours, delivering doses that could cause acute radiation sickness to unshielded colonists. But the persistent threat comes not from the sun, but from beyond. Galactic cosmic rays, high-energy particles accelerated by distant supernovae and stellar explosions, stream through the galaxy at nearly the speed of light. These particles are not easily stopped. They pass through spacecraft hulls, through habitat walls, through water, through rock. When they strike human tissue, they tear through DNA like microscopic bullets, leaving trails of cellular destruction in their wake. Unlike the radiation from X-rays or even nuclear fallout, cosmic rays carry such energy that they create cascades of secondary particles as they collide with shielding materials, sometimes making the radiation exposure inside a shelter worse than outside. The biological consequences unfold slowly, invisibly, irreversibly. Cancer risk increases substantially. Cardiovascular systems degrade faster than expected, a phenomenon observed in astronauts but poorly understood. Perhaps most troubling are the cognitive effects. Studies on mice exposed to cosmic ray analogues show persistent memory impairment, difficulty with decision-making, and neurological damage that does not heal. The brain, it seems, is particularly vulnerable. What would it mean to build a civilization where mental decline is not an affliction of age, but an inevitability of environment? And then there are the children. If humans are to truly colonize Mars, children must be born there, must grow there. But developing cells are far more sensitive to radiation than mature ones. The implications ripple forward through generations. Increased mutation rates, developmental abnormalities, shortened lifespans. We do not yet know what it means to gestate, to grow, to age under constant cosmic bombardment. The experiment has never been conducted, and the stakes could not be higher. Solutions exist in theory. Underground habitats buried beneath meters of Martian regolith could provide substantial shielding. Water, rich in hydrogen atoms, absorbs radiation effectively and could line habitat walls. Some propose generating artificial magnetic fields, bubble shields powered by superconducting magnets to deflect particles as Earth's field does. Each idea carries promise. Each also carries profound limitations. Digging underground requires massive industrial infrastructure that must somehow be transported and assembled on Mars. Water shielding demands water, a resource we have not yet confirmed in sufficient quantities near habitable locations. Magnetic shields require enormous sustained power and technology that remains largely conceptual. Even if these solutions prove viable, they confine colonists to sheltered environments, transforming the dream of walking freely on another world into existence of tunnels and barriers. The radiation on Mars is not a challenge to be overcome with optimism alone. It is a fundamental reshaping of what it means to live beyond Earth's protection. In the silence of space, particles too small to see rewrite the code of life itself. To journey to Mars is not simply to travel distance. It is to step outside the sanctuary that has sheltered every generation of humanity since life began. The question is not whether we can survive the radiation, but whether we can thrive beneath it and what we might become in the attempt. We leave behind the radiation hazards that bathe Mars in invisible danger, and now we turn our gaze inward towards something more intimate, more fundamental. Gravity. Not the gravity that holds planets in their orbits or shapes the cosmos itself, but the gravity that shapes us. Every bone in your skeleton, every heartbeat that pushes blood through your veins, every breath that fills your lungs, all of it was forged over millions of years under one specific force. Earth's gravity, 9.8 meters per second squared. The constant pressure that has sculpted human anatomy from our earliest ancestors to this very moment. On Mars, that force becomes something else entirely. Mars pulls at you with only 38% of Earth's strength. This is not simply feeling lighter, like stepping into water, or ascending to a high altitude. This is a fundamental alteration of the mechanical forces that hold your body together. Gravity is not just something we live with. It is something we are built from. And when that foundation shifts, the consequences ripple through every system, every cell, every moment of existence. Consider what happens to astronauts in microgravity aboard the International Space Station. Within the first month, their bones begin to dissolve, not metaphorically, but literally. The osteoclasts, cells that break down bone tissue, continue their work as programmed. But the osteoblasts, the cells that rebuild bone, sense the absence of mechanical stress and slow their activity. The result is a net loss of bone density at a rate of 1 to 2% per month. In 6 months, an astronaut can lose the equivalent of what an elderly person might lose in a decade. The weight-bearing bones suffer most. The hips, the spine, the legs. The very architecture that allows us to stand upright and walk across the surface of our homeworld. Now imagine Mars. Not the weightlessness of orbit, but 38% gravity. A strange middle ground where our bodies experience some resistance, but not enough. We do not yet know what happens to human bones under sustained Martian gravity. There are no experiments we can conduct on Earth to simulate it for years at a time. We have studied zero gravity extensively. We understand 1G perfectly. But 0.38G? That remains a medical mystery, a gap in our knowledge that could only be filled by sending people to Mars and observing what unfolds over months, years, decades. The uncertainties multiply when we consider muscle atrophy. Muscles, like bones, respond to the demands placed upon them. On Earth, simply standing requires constant muscular engagement against gravity's pull. Your calves, your core, the muscles along your spine, all work continuously, even when you believe you are at rest. On Mars, that work decreases. The muscles adapt by shrinking. Astronauts on the ISS follow rigorous exercise protocols, spending hours each day on specialized equipment, fighting to maintain muscle mass against the void. Even with this intense regimen, they lose muscle. Their legs thin, their hearts, also muscles, become deconditioned, pumping less efficiently because the gravitational load has vanished. What exercise routine would Mars colonists need to maintain their bodies? How many hours per day would they spend struggling against resistance machines, trying to convince their physiology that they still live on Earth? And would it even work? The cardiovascular system, evolved to pump blood upward against Earth's gravity, begins to change in space. Blood and other bodily fluids shift toward the head, creating a condition astronauts describe as feeling perpetually congested, as though suffering from a cold that never ends. The heart, sensing less resistance, shrinks slightly, becomes more spherical, loses some of its strength. Perhaps most unsettling are the changes to vision. In the microgravity of space, the fluid shift increases intracranial pressure. The eyeball flattens slightly. The optic nerve swells. Some astronauts return from long-duration missions with permanent vision changes, a condition called spaceflight-associated neuroocular syndrome. They came back different, in ways that cannot be reversed. On Mars, would the 38% gravity be enough to prevent this? Would it merely slow the process? Or would colonists gradually lose their sight over years of living under alien skies, their eyes literally reshaped by the world they chose to inhabit? These questions grow more profound when we consider not just adults who travel to Mars, but the children who might be born there. Human development is a precisely choreographed sequence of events, each dependent on the gravitational load our ancestors experienced for hundreds of thousands of generations. A fetus in the womb is constantly preparing for Earth. Its bones calcify with the expectation of 1G. Its muscles develop anticipating the resistance they will face. Its inner ear, the vestibular system that gives us balance, calibrates itself to Earth's pull. What happens when a child develops in 38% gravity? Would their bones form properly, or would they emerge fragile, unable to bear even their reduced weight? Would their hearts develop the strength needed to pump blood efficiently, or would they be weak, struggling with each beat? Would their proprioception, their sense of where their body exists in space, form correctly when the fundamental force shaping that sense is different from every human who came before them? We do not know. We cannot know without conducting an experiment that borders on the unthinkable, allowing human pregnancy and birth on Mars, knowing that the child will be a test subject in a trial we cannot undo. That child, if they survive development, would face a life of questions. Could they ever visit Earth? Or would Earth's gravity, the gravity their species evolved under, crush them? Would a Martian-born human stepping onto Earth feel their bones compressing, their heart laboring, their muscles unable to lift limbs that suddenly weigh more than twice what they're accustomed to? This raises a possibility both fascinating and melancholic. Mars colonists, if they survive, if they reproduce, if their children survive, might become something new, not through genetic engineering or deliberate modification, but through the simple, relentless pressure of living under different physical laws. After generations, they would no longer be Earthlings living on Mars. They would be Martians, adapted to their world, perhaps unable to return to ours. Humanity would split, not across oceans or continents, but across planets. Two populations, sharing ancestry but diverging in form and function, separated by a gravitational divide that cannot be bridged by willpower or technology. The thought carries a strange beauty. Evolution, continuing its ancient work on a new world. But it also carries tragedy. Every person who goes to Mars knowing they can never return home. Every child born under that rust-coloured sky who can never stand on the beaches of Earth, never feel rain falling under full gravity, never experience the world that created their species. And still, the medical unknowns persist. How does immune function change in reduced gravity? Astronauts show immune system suppression in space. Would Mars offer enough gravity to prevent this? Or would colonists live in a state of perpetual vulnerability to infection? How does wound healing proceed when the mechanical forces that normally aid tissue repair are diminished? How does pregnancy itself unfold when the gravitational cues that help position a fetus in the womb are altered? The gravity dilemma is not a problem we can engineer around with better spacesuits or stronger habitats. It is woven into the fabric of Martian existence. Every moment spent on Mars is a moment spent being gently unmade by forces that do not match the ones that made you. The human body is not a machine that operates equally well under any conditions. It is a finely tuned system, optimized across deep time for one specific environment. Mars offers 38% of that environment, and we must ask ourselves, with honesty and humility, whether 38% is enough, or whether we are proposing to send people to a world that will slowly, inexorably, reshape them into something else entirely. Not through violence, but through the quiet, persistent mathematics of physics itself. Beyond the challenges of radiation and gravity lies another fundamental barrier, one that surrounds every surface of Mars like an invisible wall. The atmosphere itself is not merely hostile, it is fundamentally incompatible with human existence. Where Earth's atmosphere cradles us in a blanket of breathable air and protective pressure, Mars offers only the faintest whisper of gas, a thin veil that barely qualifies as atmosphere at all. To build a city on Mars is to build within a vacuum wrapped in poison, where the air itself is an enemy that never sleeps, never relents, and forgives no mistakes. The numbers tell a stark story, but they reveal only the beginning of the truth. Mars's atmosphere is composed of 95% carbon dioxide, with trace amounts of nitrogen and argon, and less than 0.2% oxygen. This is not air that could be filtered or purified into something breathable. It is fundamentally wrong, chemically alien to our biology. But the composition is only part of the challenge. The atmospheric pressure on Mars averages less than 1% of Earth's sea level pressure. To stand on the Martian surface is to stand at an altitude equivalent to 100,000 feet above Earth, 3 times higher than commercial aircraft fly, in a realm where pressure suits are not optional, but the only barrier between life and immediate death. This pressure differential creates a danger that science fiction rarely portrays accurately. In films, we see dramatic scenes of suit breaches, characters gasping for air, struggling for minutes before succumbing. The reality is far more brutal and instantaneous. A significant breach in a pressure suit on Mars would trigger a cascade of physiological catastrophes within seconds. The condition is called ebulism, a phenomenon where the low atmospheric pressure causes the water in human tissue to vaporize. Saliva boils on the tongue. Moisture in the lungs begins to bubble. The tissues of the eyes and mouth swell rapidly as dissolved gases come out of solution in the bloodstream. Death would not come from suffocation alone, though unconsciousness from oxygen deprivation would occur within 15 seconds. The body itself would begin to fail in ways that are difficult to imagine, expanding, swelling, experiencing something closer to explosive decompression than the gentle fade depicted in popular media. This is not speculation. We understand these effects from high-altitude exposure incidents and rapid decompression events in space history. Every moment spent outside a habitat on Mars would carry this absolute risk. A single tear in fabric, a failed seal, a compromised joint in a glove, any of these would begin a countdown measured not in minutes, but in heartbeats. The psychological weight of this reality cannot be understated. On Earth, even in the harshest environments, a moment of exposure to the elements might be uncomfortable, even dangerous, but rarely instantly fatal. On Mars, the atmosphere itself is a predator, waiting with infinite patience for any mistake. Yet the dangers extend far beyond pressure and composition. Mars is a world of temperature extremes that would challenge even the most advanced engineering. The average surface temperature hovers around -60 degrees Celsius, though this average conceals wild variations. At the equator during summer, temperatures might climb to a relatively balmy 20 degrees Celsius during the day, almost pleasant by human standards. But as the sun sets, temperatures plunge to -70 degrees or colder. Near the poles, winter temperatures can reach -125 degrees Celsius, cold enough that carbon dioxide itself freezes out of the atmosphere and falls as dry ice snow, creating polar caps that grow and shrink with the seasons. These temperature swings place immense strain on materials, equipment, and habitat structures. Seals contract and expand. Metal fatigues. Plastics become brittle. Every component of a Martian habitat would be subjected to thermal stress cycles that have no parallel on Earth, where our atmosphere acts as a thermal buffer, moderating temperature changes and distributing heat more evenly. On Mars, the thin atmosphere provides almost no insulation. Heat radiates directly into space, and the surface cools with terrifying speed once the sun dips below the horizon. Maintaining habitable temperatures would require constant energy input, continuous heating systems running every hour of every day, drawing power that must come from somewhere, solar panels, nuclear reactors, or stored resources, all with their own limitations and failure modes. The energy requirements for thermal control alone are staggering. A modest habitat for a small crew might require as much heating as a large building in Antarctica. But unlike Antarctica, there is no possibility of simply bringing in more fuel when supplies run low. Every joule of energy must be generated on site, and any interruption in power, whether from equipment failure, dust storms, or system degradation, would begin a countdown to freezing that would leave occupants with hours at most to restore heat before temperatures inside the habitat dropped to lethal levels. And then there are the dust storms, planetary events that reveal Mars not as a dormant, peaceful world, but as a place of atmospheric violence that can engulf an entire planet. Martian dust storms can grow to cover millions of square miles, and in rare cases, the entire planet becomes shrouded in a rust-colored haze that can persist for weeks or even months. These are not mere inconveniences. They are existential threats to any settlement dependent on solar power. When a global dust storm arrives, sunlight dims to a fraction of its normal intensity. Solar panels, the most practical power source for early Mars missions, become nearly useless. Battery reserves drain. Energy must be rationed. Every system must be evaluated for what can be shut down and what must continue running to keep the crew alive. The dust storms also reveal another insidious property of Mars, the nature of the dust itself. Martian dust is not like Earth's soil. It is incredibly fine, with particles smaller than talcum powder, capable of infiltrating the smallest gaps in equipment and habitats. Airlocks would become contamination zones, where every entry and exit brings dust inside, coating surfaces, working its way into machinery, and creating a maintenance burden that would be relentless. But the physical properties of the dust are only part of the concern. Chemical analysis of Martian soil has revealed the presence of perchlorates, chlorine compounds that are highly toxic to humans. These chemicals, useful perhaps for certain industrial processes, are dangerous in living spaces. Perchlorate exposure can disrupt thyroid function, affect metabolism, and pose particular risks to developing fetuses. Any dust that enters a habitat becomes a contamination issue, requiring constant cleaning, filtration, and monitoring. The dust particles themselves, even without chemical toxicity, would pose respiratory hazards. Their fine size means they could penetrate deep into lung tissue, potentially causing inflammation and long-term damage similar to the effects of volcanic ash or industrial silica exposure. Martian dust is also highly abrasive, capable of wearing down equipment, scratching visors and solar panels, and degrading seals over time. The dust does not merely settle, it adheres through static electricity, clinging to surfaces and resisting simple cleaning methods. Everything on Mars would slowly be coated, slowly abraded, slowly degraded by the omnipresent dust. Perhaps most profound is the psychological dimension of Mars' atmosphere, a weight that cannot be measured in pascals or degrees. To live on Mars is to accept that you will never again breathe fresh air, never feel wind against your skin, never step outside without layers of technology between you and the world. Every breath would be filtered, recycled, processed through machines. Every view of the landscape would be through a helmet visor or a window. The simple human experience of being outside, of feeling weather, of experiencing the elements directly, would be forever lost. This is not merely discomfort. It is a fundamental severance from sensory experiences that have defined human existence for all of our evolutionary history. The Martian atmosphere is not simply an engineering problem to be solved with better materials or more robust systems. It is a persistent, pervasive threat that would define every moment of life on Mars. The air that sustains us on Earth is absent. In its place is a thin, toxic, frigid envelope that offers nothing but hazard. We cannot negotiate with an atmosphere. We can only endure it, contain it, and hope that our technology never fails. And in that hope lies perhaps the deepest truth about building a city on Mars. We would be building not just structures, but fortresses against a world that is, in every atmospheric sense, designed to kill us. Beneath the rusty surface of Mars, beneath the dust storms and frozen plains, lies one of the most powerful symbols of hope in all of planetary science: water ice. Orbiters trace its presence with radar. Landers scrape it from just below the soil. In the dim light of the Martian dawn, Frost sometimes coats the ground in fragile, crystalline sheets. For many, this is the key. The proof that a city on Mars is not only possible, but inevitable. Yet as we drift closer in our imagination, the illusion begins to unravel. Most of Mars's accessible water is locked in the polar regions, buried in vast slabs of ice, layered like pages in a frozen history book. These caps stretch across the high latitudes, beautiful and remote, glittering in the thin sunlight. On a map, they seem tantalizingly close. In reality, they might as well be oceans away. The poles are some of the harshest environments on the planet. Temperatures plunge far below anything recorded in Earth's coldest winters. Sunlight arrives at low angles, weak and seasonal. The atmosphere, already thin, grows even more tenuous. To reach these deposits is not only a question of distance, but of energy. Energy to travel, to drill, to melt, to purify. Extracting this ice is not like opening a faucet. It is more like mining rock. Machines must cut through permafrost, crush chunks of frozen regolith, heat them, and capture the vapor before it disappears into the near vacuum. Every step demands power, not once, but continuously, for years. In the equatorial regions where sunlight is stronger and conditions slightly more forgiving, water exists mostly as hydrated minerals and small, patchy ice deposits hidden beneath the surface. The promise is still there, but it is smaller, more scattered, less cooperative. To live here is to accept that every drop of water is the result of effort, not abundance. On Earth, we are used to the quiet luxury of invisible infrastructure. Turn a tap, water flows. Flip a switch, electricity arrives. On Mars, there is no background system humming away in the distance. There is only what we bring and what we build. We sometimes speak of closed-loop life support, as if it was simply an engineering problem, waiting for a clever design. But we have been working on this for decades. The International Space Station orbits just a few hundred kilometers above our heads, wrapped in technology more advanced than any planned Martian habitat. It recycles water, filters the air, reuses moisture from breath, sweat, and even urine. It is a masterpiece of environmental control, and yet the loop is not closed. Regular cargo ships still climb into orbit, carrying water, oxygen, spare parts, filters, and chemicals. Systems break, membranes clog, valves fail. Astronauts become custodians of a living machine that never truly relaxes. Even in the most advanced space habitat ever built, self-sufficiency remains out of reach. Not because scientists are careless, but because nature is unforgiving. On Mars, there are no regular resupply rockets arriving every few weeks. No rapid return to Earth if the machinery falters. A city that depends on a perfect recycling loop is a city that lives at the edge of a knife, trusting that complex systems will behave flawlessly, not for months, but for generations. Food, too, carries this weight of expectation. We imagine crimson domes glowing softly against the Martian night, filled with green fields of wheat and spirals of climbing beans, hydroponic trays, nutrient mists, rows of LED lights turning electricity into edible life. The idea is compelling. Grow what you need, right where you are. But Martian reality is more intricate. The soil, or regolith, is not soil in any earthly sense. It is a powder of crushed rock laced with perchlorates, salts that are toxic to humans and damaging to many plants. Left untreated, this dust is not a nurturing bed for crops, but a chemical hazard. It must be washed, processed, or replaced entirely with imported substrates. Each solution adds another layer of complexity, another step in the chain that must never fully break. Outside, sunlight is weaker than on Earth. filtered by distance and a thin, dust-filled sky. A greenhouse relying purely on natural light would face long, dim winters and frequent storms that blot out the sun for weeks. Artificial lighting can compensate, but only by consuming vast amounts of power that must itself be generated, stored, and maintained in a world where dust settles on every panel and cold seeps into every wire. Within the safety of pressurized habitats, the air, pressure, and humidity must be held stable for plants as well as people. Carbon dioxide must be managed as both waste and resource. Nutrients must be cycled without interruption. A greenhouse on Mars is not a garden. It is a carefully tuned ecosystem perched above a desert of vacuum and ice. Even if we solve these problems, food production at city scale demands more than a handful of experimental greenhouses. It requires an agricultural infrastructure, seed storage, pest control, pollination strategies, waste processing, nutrient recovery. Every lettuce leaf, every grain of rice, every soybean is the result of a long chain of careful decisions. A chain that, on Mars, has no backup supplier over the horizon. Beyond water, air, and food lies the quieter, heavier demand of civilization, industry. A city is not just homes and gardens. It is pipes and wires, beams and bolts, plastics and glass. It is tools to repair tools, machines to build replacement parts, kilns and furnaces and chemical reactors that turn raw dust into usable materials. To be truly self-sufficient, a Martian city must do more than survive. It must replicate its own foundations. Consider the path from rock to radio. First, mining equipment is needed to dig and crush the regolith. Then, refining systems must separate useful metals from useless ones, extracting iron, aluminum, copper. Smelting requires heat, often intense heat, which demands concentrated energy and durable containment. From metals, we forge machines. From machines, we assemble factories. From factories, we produce the delicate, intricate components that power electronics and life support. Plastics require hydrocarbons and complex chemical feedstocks. Glass needs purified silica and controlled furnaces. Semiconductors demand extreme cleanliness, precision, and multiple layers of manufacturing sophistication. On Earth, each of these steps is distributed across continents, supported by millions of workers and centuries of accumulated knowledge. On Mars, the city must become all of these things at once. This is the bootstrapping problem. Factories to build factories, tools to make tools, systems that must exist before they can be built. Early settlers will rely heavily on equipment brought from Earth, modular habitats, prefab reactors, specialized drills. But each imported item has a limited lifespan. Seals degrade, bearings wear down, electronics succumb to radiation and age. To replace them locally is not one task, but many, stacked like layers of an invisible pyramid. At the base, mining and power. Above that, refining, chemistry, metallurgy. Higher still, manufacturing, machining, assembly, quality control. At the very top, the delicate, life-critical components that allow the entire structure to function. No single mission, or even a handful of missions, can compress the entirety of Earth's industrial history into a decade of cargo launches. What we call self-sufficiency here at home is actually an emergent property of an immense interconnected web of processes and skills. Recreating even a fraction of that web on another world is not merely ambitious, it is generational. When optimistic timelines speak of Mars cities becoming self-sustaining in a few decades, they often measure only in human years. But the systems we depend on, ecological, industrial, technological, operate on deeper timescales. To make Mars truly independent is to reenact in compressed form, a journey that took humanity thousands of years on Earth. Step by step it may happen. Early outposts relying on near-total supply from Earth, then partial recycling, limited local manufacturing, experimental agriculture. Slowly, more items produced on Mars, fewer launched across the void. Each improvement fragile, each gain reversible if critical expertise is lost or a key facility fails. In this light, a realistic path to genuine self-sufficiency does not look like decades. It begins to resemble centuries. Not because humans are incapable, but because complexity has a weight of its own. We are not simply moving bodies to another planet. We are attempting to transplant the entire invisible scaffolding of a technological civilization into an environment that offers no natural safety net. The dream of a Martian city that no longer needs Earth is powerful. It speaks to our longing for independence, for security beyond a single fragile world. But for a very long time, any settlement on Mars will be less a separate civilization and more a remote, vulnerable outpost. An advanced research station at the edge of a vast silent frontier. In the darkness between planets, ships will continue to sail, carrying tools, medicine, replacement parts, and knowledge. The lifeline cannot be cut simply because we wish it so. Instead, it will thin slowly over generations as new capabilities emerge, as local expertise grows, as the Martian web of industry and ecology gains strength. Until then, the illusion of self-sufficiency remains just that, an illusion. Beneath it lies a more subtle, humbler truth. That if we go to Mars and try to stay, we will not be building a second Earth. We will be building an elaborate, delicate collaboration between worlds. A collaboration measured not in flags planted, but in supply ships, maintenance logs, and the quiet hum of machines working tirelessly in the thin red air. Time behaves strangely on the journey to Mars, but it behaves even more strangely once we arrive. On Earth, distance is something we measure in miles, in hours of flight, in the ticking hands of a clock. But on Mars, distance from home will be measured in silence. Not the comfortable silence of a quiet room, but a stretched, delayed, distorted silence that turns every conversation into a message in a bottle. At its closest approach, Mars is still tens of millions of miles away from Earth. At its farthest, it drifts out to more than 200 million miles. Light, the fastest thing in the universe, takes between 4 and 24 minutes to cross that gulf, which means a simple, "How are you?" could take nearly an hour to be asked and answered. There will be no phone calls with family, no real-time video chats, no immediate reassurance when something goes wrong. Instead, every communication becomes a kind of echo. You speak, and minutes later, your voice arrives as a faint digital ghost on another world. They respond, and for long stretches of time, you wait in a kind of suspended thought, your words already gone, their reply not yet born. The illusion of presence that we take for granted today, live streams, instant messages, the hum of a connected planet, falls apart on Mars. The colony will exist in a different tempo of time, asynchronous with Earth, like two hearts beating out of phase. Even if messages flow constantly, they will never be conversations, only monologues that occasionally intersect. Psychologists already know that delayed communication changes how we relate to one another. Misunderstandings grow in the gaps. Emotional nuance is harder to read in text. On Mars, a colonist having a difficult day cannot simply call home and hear a familiar voice respond immediately. Instead, comfort, advice, or even a joke arrives out of sync with the moment it was needed. The result is subtle but cumulative. an ever-present sense of being slightly out of step with the world that once defined you. And inside the habitat, another kind of distance takes hold. Mars will not offer sprawling cities or endless horizons of green. For most colonists, life will unfold inside modules, tunnels, and pressurized rooms measured not in miles, but in steps. A handful of rooms, shared corridors, recycling systems humming softly in the background, and always the reminder that a thin barrier separates breathable air from a killing vacuum of CO2 and dust. We have small windows into this future from Earth. Antarctic research stations where the sun disappears for months at a time, submarines gliding silently beneath the ocean, their crews sealed in steel. Isolation studies in sealed habitats in Hawaii or on the slopes of volcanoes, where volunteers simulate Martian life. Across these very different environments, a similar pattern appears. At first, there is novelty, a sense of mission, curiosity about the routines, the technology, the new rhythm of life. Then slowly, time begins to stretch. The same faces appear at every meal. The same walls greet you every morning. The same limited sounds, smells, and sights repeat, looping endlessly like an environment on replay. Even in the most well-designed Antarctic stations, where crews can step outside in protective gear and breathe the cold air, people report something that psychologists call psychological closing. Their world shrinks, not just physically, but mentally. Thoughts focus on the immediate, on the small dramas of the station. The rest of the planet feels distant, abstract, almost unreal. On Mars, that effect deepens. There is no true outside in the way we know it. Stepping out onto the surface requires a suit, a checklist, an airlock cycle. Every excursion is planned, monitored, constrained by oxygen levels, radiation exposure, and dust conditions. The landscape, no matter how vast, is always experienced through layers of protection, like looking at a painting through glass. And yet, in that hostile stillness, another psychological shift waits. Many astronauts returning from orbit describe the overview effect, a sudden overwhelming awareness of Earth as a fragile, glowing sphere suspended in darkness. Borders vanish, petty conflicts fade. There is only a single shared home. On Mars, that effect does not vanish. It reverses. From the Martian surface, Earth will never fill the sky. It will not rise and set in the way our moon does. Instead, it will appear as a small, bright point, barely more than a star, sometimes lost in the glare of the sun or hidden behind dust storms. To look up and recognize that tiny dot as everything you have ever known, every memory, every ocean, every forest, every person you love, will be a moment both profound and unsettling. The overview effect compresses our sense of separation. The Martian perspective will expand it beyond anything we have yet experienced. For some, this may bring a sense of spiritual awe, a feeling of participating in a story far larger than an individual life. For others, it may bring a different realization, that they have stepped onto a world that may never allow them to return. Medical risks, economic realities, mission constraints, all of these could mean that Mars is not a destination, but a one-way horizon. It is one thing to read that in a mission briefing. It is another to feel it in your bones, lying awake beneath a rust-colored sky, knowing Earth is no longer a place you can simply go back to, but a moving point of light. Inside the habitat, the challenges become more intimate. Small groups in confined spaces do not remain neutral for long. On submarines, in polar stations, and on space stations, researchers have documented what they call third-quarter syndrome. Morale often dips dramatically after the halfway point of a mission, when the initial excitement has faded, but the end is still far away. Minor annoyances swell into major grievances. Different cultural backgrounds, habits, and personality traits rub against one another. In most environments on Earth, a person can step outside, take a walk, or simply leave a difficult situation. On Mars, there is no outside that is safe to retreat into. Every relationship is inescapable. Every conflict is recycled, like the air, through the same few rooms. Command structures and psychological screening can help, but they cannot erase human nature. Someone who chews too loudly, uses too much water, always asks the same questions, or structures their day differently may become a constant irritant in an environment where there is nowhere else to focus your attention. Over months and years, these tiny frictions can erode collaboration in ways that no engineering system can easily repair. Even the landscape offers no real relief from repetition. Imagine waking up day after day knowing exactly what you will see if you look outside. A dry horizon, muted in colors of rust and tan, broken by rocks and dunes, under a thin salmon sky. Mars is beautiful, but it is not lush. It does not change quickly with seasons like Earth. The monotony of the view, combined with the monotony of the habitat, could create a kind of sensory drought. Our brains evolved in forests, along coasts, in cities full of noise and motion. We are adapted to variety, to unexpected sights, smells, and sounds. When those are stripped away, the mind does not simply rest. It begins to generate its own stimulation, sometimes in the form of daydreams and creativity, and sometimes in the form of anxiety, rumination, or even hallucinations. Mental health professionals understand these risks. Yet on Mars, providing care will be as constrained as every other resource. A colony may have 1 or 2 trained psychologists, perhaps a psychiatrist, perhaps none at all in the early years. Their role will be complex. They will be both caregivers and neighbors, therapists and teammates, sharing the same stresses as the people they are trying to help. Telemedicine from Earth can provide consultation, but every conversation with a specialist will carry that same communication delay. In emergencies, suicidal thoughts, panic attacks, psychotic breaks, waiting 20 minutes for a reply is an eternity. Colonists will have to make decisions in the moment with incomplete information, using protocols designed far away for situations no one has truly experienced before. Medications, too, become a question of time and scarcity. Antidepressants, anti-anxiety drugs, sleep aids, antipsychotics. All of these have shelf lives, storage constraints, and side effects that may behave differently in reduced gravity and altered day-night cycles. Resupply missions can send more, but not instantly. A delay in a launch window or a failed shipment could mean months without access to a critical treatment. And beneath all of this lies something more subtle: the stigma that still surrounds mental health. In a small, tightly monitored colony where every role is essential, admitting that you are struggling may feel dangerous. People may hide their symptoms, push through exhaustion, suppress their fears, all in the name of not letting the team down. The result is a psychological abyss that is not created by any single factor, but by the convergence of many: distance, delay, confinement, monotony, responsibility, and the irreversible nature of the journey. Mars challenges our technology, our biology, and our engineering. But perhaps its most unforgiving test will be of something less tangible: the quiet, private space of the human mind, held for years within a fragile shell of metal and air, under a sky that will never quite feel like home. On Earth, crisis arrives with a familiar sound: a phone dialing, a siren rising in the distance, the quiet efficiency of a hospital waking up around a single human life. Lights flicker on, monitors beep, teams assemble. Within minutes, a stranger can be surrounded by more medical technology than most of human history ever knew. On Mars, there is no siren, no ambulance, no emergency room waiting like a safety net beneath our every reckless moment. There is only a small room, or a limited set of tools, and a 7-month delay between the question and any hope of an answer. In the quiet halls of a Martian settlement, medicine would not be a sprawling system. It would be a single fragile node, a few trained crew, a closet of supplies, a handful of manuals and pre-recorded instructions. When something goes wrong, there is no transfer to a bigger hospital, no call for a specialist to scrub in, no helicopter to a better equipped city. The hospital is whatever you brought with you, and whatever you remembered to practice before you left. On Earth, the variety of medical expertise is almost invisible because it is everywhere. Surgeons, anesthesiologists, cardiologists, neonatologists, radiologists, pharmacists. Decades of training, thousands of hands, all woven into a dense fabric that catches us when we fall. On Mars, that fabric thins to a single thread. Maybe there is one physician, a paramedic, a nurse with additional training, perhaps one crew member with surgical experience, but no one human mind can replace the layered redundancy of Earth's medical infrastructure. A generalist for everything becomes a heroic idea. But biology is not impressed by heroics. It simply fails in the ways it always has. Appendicitis, a ruptured ectopic pregnancy, a perforated ulcer. On Earth, these are urgent but routine emergencies. On Mars, they are complicated gambles with improvised protocols and finite supplies. Each decision carries a weight measured not just in risk, but in isolation. There is no second opinion walking down the hall, only a delayed voice, minutes away by radio and months away by flight. Surgery itself becomes an entirely different frontier. Our instruments, our training, even our hands are accustomed to a world where gravity quietly cooperates. Blood falls, fluids pool, smoke from cauterization rises and is pulled away. On Mars, gravity is only a whisper, 1/3 of what it is on Earth. The choreography of an operation changes in ways we are only beginning to imagine. When a scalpel opens skin, the blood does not behave as expected. Droplets can cling, drift, bead in slow, delicate arcs. Fine mist from suction and irrigation may linger in the air, carrying microscopic life with it. The sterile field, so carefully maintained in Earth's operating rooms, faces a silent new adversary. A room where particles do not settle, they float. Ventilation systems must do more than bring air. They must capture every wandering drop, every invisible threat, without disturbing the delicate hands trying to repair a human body. Surgical tools may need to be magnetized, tethered, or redesigned, so they do not gently drift away at the worst possible moment. Even anesthesia, the invisible guardian of modern surgery, becomes fragile. On Earth, hospitals carry large stocks of anesthetic gases, narcotics, sedatives, reversal agents. On Mars, every vial is a countdown. Every ampule used is one that cannot be easily replaced. Supply ships are rare. Manufacturing complex pharmaceuticals on demand is still a dream, not a daily reality. A difficult operation might burn through weeks of carefully rationed medicines in hours. One catastrophic emergency could deplete the drugs needed for dozens of smaller procedures. The calculation shifts from, can we save this person, to, what will it cost the entire colony if we try? It is here that the quiet, logistical nature of medicine reveals itself as something far more profound. On Mars, health is not just a personal condition, it is a communal resource. Even medications that make the journey safely face another subtle enemy: time and radiation. Pharmaceuticals are surprisingly mortal. Many degrade slowly even on Earth, losing potency or producing harmful byproducts if stored for too long or under the wrong conditions. On Mars, this decay plays out under a thinner atmosphere, increased background radiation, and a supply chain measured in years. Cosmic rays and solar particles, which slip more easily through Mars's weak shielding, can break chemical bonds in complex drugs. Biologics, insulin, certain cancer therapies, and advanced antibiotics are particularly delicate. Refrigeration helps, shielding helps, but nothing halts decay entirely. The most cutting-edge medicines, those tailored to specific cancers or immune conditions, often require sophisticated cold chains and manufacturing facilities that sprawl across continents. Shrinking that to a few rooms in a habitat is not just an engineering challenge, it borders on alchemy. A colony could manufacture simple compounds, painkillers, basic antibiotics, saline, perhaps some anesthetics. But the full orchestra of modern pharmacology, thousands of specialized molecules for rare conditions and edge cases, would be out of reach for many years, perhaps decades. In such a world, chronic illness transforms from a manageable part of life into a constant negotiation. Consider diabetes. On Earth, many people live long, full lives with daily insulin injections, continuous glucose monitors, emergency glucagon, routine lab work. On Mars, insulin must be kept cold, stable, and sterile for months and years. If a shipment is delayed, if a freezer fails, if a batch degrades unseen, the margin between stability and crisis evaporates, or heart disease. Pacemakers and stents rely on precise implantation, follow-up checks, and sometimes emergency interventions when something goes wrong. A sudden arrhythmia that would trigger a brief hospital stay on Earth could become a slowly unfolding tragedy on Mars, managed with whatever equipment happened to fit into a launch manifest. Cancer care, too, shifts from a landscape of options: surgery, radiation, immunotherapy, targeted drugs, to a narrow ridge. Some surgeries may be possible, a few chemotherapy regimens perhaps, but the idea of full-spectrum oncology, with weeks of precisely calibrated treatments and imaging, collides with the harsh arithmetic of volume, mass, power, and expertise. All of this converges on one of the most emotionally charged questions of any Martian settlement: birth. On Earth, pregnancy is both ordinary and astonishing. It is also, quietly, medically complex. Modern obstetrics wraps pregnancies in layers of ultrasounds, blood tests, emergency protocols. Operating rooms stand ready for cesarean sections. Neonatal intensive care units glow softly with incubators, ventilators, and carefully titrated drugs. On Mars, every pregnancy would be high risk by default. We do not know how human embryos develop in low gravity. We do not know how Mars's radiation environment shapes fetal growth, or how partial gravity affects the pelvis, the uterus, the placenta. We do not know whether bones and muscles, still forming, will respond to 1/3 gravity with adaptation, or with vulnerability. Routine complications, preeclampsia, hemorrhage, obstructed labor, cord prolapse, are only routine because Earth carries a vast infrastructure built to respond to them. On Mars, each one is an emergency that might demand a surgeon, an anesthesiologist, units of stored blood, a neonatal ventilator, and a crash team that does not exist. A difficult labor at 3 a.m. on Mars is not a story of flashing pagers and bustling corridors. It is a small group of people, tired, frightened, doing their best with limited tools, knowing that there is no backup coming over the horizon. If a newborn requires intensive care beyond the simplest support, there is no transfer to a specialist hospital. The settlement is the first and last line of defense. This leads to an uncomfortable but unavoidable question. Should a place with such limited medical capability bring new life into it at all? The ethics of reproduction on Mars extend beyond romance or personal desire. They seep into policy, into planning, into the quiet agreements that shape a community. Is it right to encourage pregnancy in an environment where both mother and child face unknown and potentially severe risks? Who decides if a pregnancy can be supported safely? What if a complication arises that Earth medicine could easily handle, but Mars cannot? Behind each of these questions lies another, softer one. What does it mean to be responsible for a life when you have intentionally left behind most of the tools needed to protect it? A Martian city is often imagined as a beacon of human expansion, a symbol of resilience and ingenuity. But every radiant dome and gleaming pressurized corridor would also be filled with bodies that ache, bruise, break, and age just as they do on Earth. Bones will fracture, hearts will falter, minds will struggle, cells will mutate. The difference is not in what can go wrong, but in how alone we are when it does. On Earth, a medical emergency pulls on a vast web, summoning resources from across a city, a country, sometimes the world. On Mars, that web shrinks to the reach of your own outstretched hand. And beyond that hand, 7 months of empty space. The journey to Mars is often drawn in lines of fuel and flight paths, rockets and radiation. But there is another map we rarely unfold. It is written not in miles, but in money. Not in trajectories, but in trade-offs. Before a single brick of a Martian city is placed into the thin red dust, a quieter question hangs in the vacuum between worlds. Who pays for Mars? When we imagine a city beneath the pale salmon sky, we rarely imagine the invoices. Yet if we try to give that dream a number, the figures begin to swell like distant gas giants on the horizon. Some estimates, on the most optimistic edge of possibility, place a basic, functioning colony at around $100 billion. Others, more cautious, drift into the realm of trillions. Not for terraforming, not for sprawling domed cities shimmering with fields and rivers, but simply for a fragile foothold. Habitats that barely sustain life, machines that barely keep up. A community that always lives one failed shipment away from catastrophe. To put such numbers into scale, we can look back at what humanity has already done. The International Space Station, a small outpost in low Earth orbit, costs more than $100 billion to assemble and maintain. It supports at most a handful of people at a time, orbiting a mere few hundred kilometers above Earth, close enough to see cities at night and clouds drifting below. And even there, even with near constant resupply from the planet's surface, every litre of water, every tool, every replacement filter is precious. Now stretch that distance from a few hundred kilometers to tens of millions. Replace a quick 6-hour ride to orbit with a 7-month crossing through deep space. Replace the comfort of Earth's magnetic field and quick emergency return with the sharp finality of being utterly on your own. The costs do not just increase, they transform. A Mars city is not one project. It is a stack of projects, each heavier than the last. Launch systems, cargo fleets, life support factories, fuel depots, landing craft, surface infrastructure, radiation shelters, power grids, medical facilities, communication networks, and the quiet, invisible layers of logistics beneath them all. Each of these speaks its own language of billions and trillions. Each demands not just to be built once, but to be maintained, upgraded, and endlessly supplied. And yet, after all this, another question rises gently like a distant moon. What does Mars give back? On Earth, cities grow where trade makes sense, ports on coastlines, towns where rivers meet, markets at crossroads. Value flows in and out, and the city sustains itself. Mars offers no such easy exchange. Its iron-rich sands and frozen water sound promising, but only if you are already there. The cost to lift even a single kilogram of material off the Martian surface and deliver it back to Earth would be immense. Any metals, minerals, or ices that lie beneath the Martian crust are, for all practical purposes, locked away behind a paywall, written in rocket fuel and time. We sometimes imagine Martian mines, robotic drills chewing ancient rock, ships returning to Earth heavy with exotic resources. Yet nearly every element we might hope to find on Mars already exists on Earth, often in greater abundance and far easier to reach. As of now, there is no resource on Mars we know of that could survive the brutal economics of transport. No platinum-rich vein, no miracle isotope that would pay back the cost of a transplanetary supply chain. So, if Mars cannot be mined for profit, perhaps Mars can be sold as something else. A frontier, a brand, a sanctuary, a monument. Here, the economics become more abstract. A colony might be funded not because it makes money in the traditional sense, but because it embodies a story of destiny, of survival, of human greatness. Investors might one day buy shares in Martian real estate. Companies might sell the romance of residency, tourism, and off-world citizenship. But beneath the stories, the equations remain. Habitats must be paid for. Fuel must be bought. Every passenger seat must be justified in the quiet language of balance sheets. Then, another layer appears. The colonists themselves. Who are the people who go to Mars? Are they explorers, citizens, employees, or something else entirely? Do they pay for their passage as one might pay for a ticket on a great ship, indebting themselves to corporations or governments for a lifetime? Or are they paid to go, specialists recruited and funded as part of a national or planetary project? Where do their rights begin and where do they end? If a colonist on Mars is injured, who is responsible? If laws are broken, whose laws are they? Earth's nations, a multinational treaty, a corporate charter, a new Martian constitution written in the dust by the first arrivals. On Earth, we have centuries of legal tradition shaping who owns land, who owes taxes, who has power. On Mars, all of that becomes faint and uncertain. Space law today was crafted for satellites and short-term missions, not for children born under another sun. The first true Martian city would not only be an engineering experiment, it would be a political and legal experiment as well, one that demands oversight, courts, governance, and agreements, all of which have their own costs, both in money and in trust. And still, behind it all, hums the constant whisper of logistics. A Martian colony is, at least at first, unable to provide almost everything it needs. Tools wear out, electronics fail, medical supplies expire, air filters clog, machines that make air and water need spare parts of their own. To keep even a small outpost alive, Earth must send ship after ship, a continuous lifeline arcing across space. Each resupply mission, the rockets, the fuel, the cargo, the launch facilities, the teams on the ground, costs not millions, but billions of dollars. And these shipments are not occasional. They must be regular, predictable, unwavering, synchronized with rare planetary alignments that open launch windows only every 26 months. Miss one, and a colony's inventory spreadsheets slowly turn into countdown clocks. In this fragile chain, a storm on Earth, an economic crisis, a change in government priorities, or a single catastrophic launch failure could ripple outward and arrive at Mars months later, not as a news headline, but as empty shelves. Missing medicines, absent machine parts, a reserve of oxygen filters that suddenly looks too small. When we speak of who pays for Mars, we often think of budgets and taxes, of private companies and rich investors. But there is another cost, harder to see: opportunity. Imagine, for a moment, what else $100 billion could do, or $1 trillion. On Earth, these amounts could transform energy systems, eradicate specific diseases, rebuild coastal cities, fund scientific research for generations, or bring clean water and sanitation to vast regions. They could feed minds with education and protect ecosystems that took millions of years to evolve. None of this means Mars is unworthy of pursuit. But it reminds us that every rocket launched toward the red planet is not just a step forward. It is also a step not taken somewhere else. The question becomes not simply, can we pay for Mars, but what are we choosing not to pay for so that Mars might exist? So far, despite ambitious speeches, striking concept art, and earnest timelines, no government or corporation has locked itself into the full, binding costs of a true colony. Space agencies commit to probes, rovers, orbiters, and perhaps crewed missions that touch the surface and return. Companies promise plans and prototypes, rockets and capsules. But a permanent city, thousands of people, decades of guaranteed resupply, governance, healthcare, education, and infrastructure remains, for now, an aspiration more than a contract. Budgets shift from year to year. Political winds change. Economic downturns tighten the flow of funds. Even the most enthusiastic backers must weigh public opinion, profits, and the quiet realities of risk. It is far easier to fund a mission that lasts years than a settlement that demands support for lifetimes. In this way, the economics of Mars are not just about dollars or credits. They are about time, commitment, and uncertainty. To build a city on Mars is to promise future generations that, regardless of what happens on Earth, recessions, wars, climate change, new technologies, the shipments will keep coming, the bills will continue to be paid, the experiment will not be abandoned halfway. Standing in the stillness of that thought, the dream of a Martian city becomes something different. Less a gleaming utopia under glass domes, more a fragile bridge that must be held up, year after year, by countless hands and minds on a distant world. We often imagine the first colonists watching Earth as a pale blue star in their sky, but perhaps the more difficult image is the reverse. People on Earth, watching budget lines and launch schedules, keeping that distant light alive on a world that can give them nothing tangible in return. In that tension, between wonder and cost, between aspiration and responsibility, the economics of Mars reveal themselves. Not as a simple equation, but as a long, quiet negotiation between what we dream and what we are willing, together, to sacrifice. And just beyond the ledger, waiting in the faint red twilight, lie even harsher questions. How do we build what we cannot repair? How do we plan for disasters when the nearest help is months away? To answer those, we must leave the balance sheets behind and step into the machinery itself. On the glossy brochures and inspiring keynote stages, a Martian city looks simple. A few domes, some solar panels stretching into the rust-red distance. Perhaps a greenhouse, glowing faintly against the endless night. The diagrams are clean, the arrows are neat, the systems are robust and redundant. But engineering on Mars is not a brochure. It is a continuous bargain with a planet that offers nothing for free. On Earth, we live inside a vast safety net we rarely notice. If your heater fails, the air outside still has oxygen. If the lights go out, you can open a window. Your life does not depend on the precise alignment of pumps, seals, software, and filters humming in perfect synchrony. On Mars, it does. Every breath in a Martian habitat would pass through machines, oxygen generators, carbon dioxide scrubbers, pressure regulators, thermal control loops, each one a single point of failure, even if we surround it with backups. Because the brutal arithmetic of survival never changes. If the air system stops, you do not have days to figure it out. You have minutes. Life support becomes less a system and more a beating mechanical heart, one that can never skip a beat. Airlocks must seal perfectly every time. Water must endlessly cycle through filters and membranes, distilled, purified, and returned. Carbon dioxide must be captured before it quietly builds to lethal levels. Each valve, each sensor, each O-ring becomes part of an invisible chain. If any link snaps, the chain does not sag. It breaks. Power follows the same rule. On Mars, night falls for long frozen hours. Dust storms can cloak the sun for weeks, sometimes months, turning once bright solar farms into fields of dim, useless glass. Batteries drain, temperatures plunge, the colony's warmth, its lights, its communications, its air, all ride on an electrical lifeline that cannot fail. A cracked cable, an inverter short, a battery cell gone into runaway. On Earth, these are inconveniences. On Mars, they are the first dominoes in a chain you might not be able to stop. The promise of redundancy sounds comforting. Multiple generators, multiple habitats, multiple life support units. But redundancy is not magic, it is mass. Every spare pump, every replacement filter, every backup circuit must be built on Earth, tested, packed, launched, and landed millions of kilometers away. Each kilogram competes with food, medical supplies, scientific equipment, and the dreams of the mission planners. You cannot have infinite backups in a place that charges you in fuel and physics for every gram you bring. Engineering a Martian city is not the act of designing a few heroic machines. It is designing an ecosystem of millions of interacting parts, each one aging, wearing, drifting out of specification. Plastic becomes brittle in the cold. Lubricants evaporate in thin air. Metal expands and contracts in daily temperature swings so severe they can open microscopic cracks that grow silently with every sunrise and sunset. The tyranny of complexity is quiet. It lives not in dramatic explosions, but in tiny misalignments. A pressure sensor that reads slightly low. A software patch that introduces a 1 in a million glitch. A filter that clogs a few days earlier than expected. None of these feel catastrophic in isolation. Yet a colony does not live in isolation. It lives in the sum of all its margins. On Earth, when that complexity turns against us, we reach for help. A technician arrives in a truck. A spare component is overnighted from a warehouse. A team of specialists gathers in a control room, armed with tools and spare parts. Even our most remote research stations sit on a planet where rescue is difficult but possible. On Mars, there is no next-day delivery, no global warehouse, no technician flying in from another continent. There is only what you brought, and what you can make slowly with whatever limited manufacturing you manage to ship across space. Imagine standing in a small habitat, air thinly contained by layers of composite and aluminum. A pump fails. You know exactly what replacement you need, down to the serial number. You can even see it in a repair manual on a tablet screen. But it is not on Mars. It is on Earth, 7 months away by rocket, and no one can launch it in time. Every design review, every engineering meeting becomes dominated by one haunting question. If this breaks, can we fix it with what we have? Not in theory, but in practice, with tired hands, limited tools, and a clock that never stops. And then there is the dust. Martian dust is not like the soft soil of a garden, or even the grit of a desert on Earth. It is the product of billions of years without rain, without flowing water to smooth its edges. Tiny, jagged particles ground from volcanic rock and shattered meteorites, many infused with reactive chemicals like perchlorates. It behaves more like powdered glass than harmless sand. It infiltrates everything. Dust will cling to spacesuit joints, grinding them down with every step. It will settle into seals designed to keep precious air inside and poisonous atmosphere out, slowly eroding their perfection. It will drift into filters, clogging them sooner than they were meant to fail. It will coat radiators meant to release heat, insulating them, forcing systems to run hotter and closer to their limits. Even the act of going outside to explore, to maintain, to repair, becomes a negotiation with a planet-wide contaminant that rides in on boots, gloves, and tools. Each airlock cycle becomes a small failure of cleanliness, a little more dust slipping into the fragile mechanical lungs that keep the colony alive. We can design better seals, smarter filtration, more durable materials. And yet, in the long timeline of a permanent settlement, the question is not whether dust will get in. It is how long it takes before the accumulated burden of that dust, on bearings, on fans, on suits, on solar panels, tips some hidden equation from safe to unsafe. The true danger is not the single dramatic failure, but the cascade. A habitat wall does not simply rupture without warning. Instead, a small leak appears, maybe in a section weakened by micrometeorite damage and thermal cycling. The leak forces the compressors to work harder to maintain pressure. They consume more power. The increased power draw pushes the energy system closer to its limits. To compensate, lights are dimmed, heating is lowered, batteries are cycled more deeply. The colder environment causes condensation in an electrical panel, corroding a connector. That connector feeds a sensor, which now reads erratically. The software, trusting the faulty sensor, mismanages a piece of equipment. A pump overheats and fails. The colony sees the failure of the pump. It does not see the quiet thread that began with a pinhole leak in the hull weeks ago. Complex systems fail in complex ways. On Mars, there will be no forensic teams from distant universities travelling in to study the wreckage. No global commission piecing together what went wrong over years. The colonists themselves would be both the witnesses and, potentially, the victims. Back on Earth, companies and agencies promising Martian cities must choose their words carefully. Marketing decks speak of scalability, modular design, and fail-safe systems. Animations show smiling colonists strolling under glass domes, hydroponic gardens shimmering with green. The camera rarely lingers on the back rooms, the cramped maintenance corridors, the filter rooms, the servo racks, the cluttered workbenches where someone will sit at 3 a.m., tightening a bolt that absolutely cannot come loose. Engineers know those rooms. Flight controllers know the tension of watching a single number on a screen. Temperature, pressure, voltage slowly drift toward a line marked in red. Space, even in low Earth orbit, is unforgiving. Satellites fail. Space stations age. Valves stick. Lines freeze. Every success we celebrate has come wrapped in layers of contingency plans, safety margins, and last-minute improvisations. Now stretch that fragility across 225 million kilometers of emptiness, with a 7 to 20-minute delay on every radio command, and no chance of coming home in an emergency. The honest engineering reality of a Martian city is not that it is impossible, it is that it is merciless. It will demand systems that are not only reliable, but repairable, with tools and materials that do not yet exist on that world. It will demand colonists who are not only scientists and explorers, but mechanics, machinists, electricians, and software debuggers, ready to diagnose failures in the dead of night while the rest of the colony sleeps. And even then, despite all the planning and heroism, there will be moments when the margin between life and death narrows to a single failing component, a single miscalculated load, a single overlooked crack. On the glossy posters, Mars looks like a blank canvas for human ambition. In the quiet reality of engineering, it is more like a tightrope stretched over a vacuum. Each step is possible. Each step is also final. Beyond the dreams and the slogans lies a simple truth. To build a city on Mars is to accept that what can go wrong eventually will. The question is not whether we can design around that truth, but whether we are prepared to live inside it. We imagine the first Martian city as a triumph, a glittering dome beneath a salmon sky, sunlight diffused through thin air, habitats humming softly, greenhouses glowing like lanterns in the dust. In our stories, it is a symbol of progress, a declaration that humanity has stepped beyond its cradle. But before we build anything on this distant world, we have to confront a quieter question. Not can we, but should we? As our imaginary spacecraft orbits Mars, slowly tracing the curve of its rusted deserts, we look down at a planet that has never known us. No factories, no plastic, no radio noise humming through its sky. Just stone, ice, and silence, shaped only by wind and time. For billions of years, Mars has existed without our touch, and now we talk openly about changing it forever. In the stillness above this world, ethics stops being an abstract debate. It becomes a landscape, stretching beneath us like an unanswered question. One of the first concerns is planetary protection. The idea that worlds like Mars are not just destinations, but laboratories of cosmic history. When a spacecraft lands there, it does not arrive alone. Traces of Earth come with it. Bacteria that survive sterilization, fungal spores hidden in seams, organisms that have evolved for our planet, not this one. If Mars is completely sterile, then the main risk is that we overwrite a unique, untouched environment with our biology. But if Mars is not sterile, if somewhere beneath its surface, in salty brines or buried ice, there are remnants of ancient life or fragile ecosystems clinging to existence, then contamination is something deeper. It is the potential erasure of a separate origin story. We search Mars for signs that life can begin twice in one solar system. A second genesis would change our understanding of biology, evolution, even our place in the universe. But if we rush to colonize, seeding the soil with microbes from Earth, the evidence could blur. A Martian microbe and a hardy Earth bacterium, both microscopic, both simple. If they mix, how do we ever untangle what came from where? Future scientists, trying to read the history written in Martian rocks and ice, might find only a smudged page. In the language of space agencies, this is called forward contamination. The phrases sound technical, calm, but beneath them is a simple, almost childlike question. When you arrive at a place that may hold its own secrets, is it right to stomp through it with muddy boots? Some propose strict containment zones, scientific preserves on Mars that no settlement is allowed to touch. Others imagine we should wait, hold back colonization completely until we are certain we understand the planet in its wild state. Yet certainty, in science, is elusive. If we demand total knowledge before action, we may never act at all. And still, the rockets are being built. Even if we solve the problem of protecting Mars from our biology, another ethical riddle waits in the dust: the people born there. It is one thing to volunteer for a one-way mission, to sign your name on a form knowing you might never see Earth again. Adults can choose that. They can weigh the risks and decide that the view of Phobos rising over the horizon is worth everything it costs. But a child born under a weaker gravity in a confined settlement does not sign anything. On Mars, human development will be an experiment without a control group. Lighter bones, altered hearts, different muscle growth. A lifetime inside controlled atmospheres, shielded tunnels, filtered light. Their bodies may never be able to safely handle Earth's heavier gravity or its pathogens. For them, Earth might exist only as a blue star in the sky and a collection of stories. Ethicists sometimes ask, can someone truly consent on behalf of another person to live in a place they can never leave? To be, in a literal sense, planetary citizens by birth and biology, bound to a world they never chose. We accept that children born in remote regions, on ships, in polar research stations, inherit circumstances. But Mars is different in scale and irreversibility. A Martian-born person may watch videos of oceans they cannot swim in, forests they cannot walk through, rain they can never feel on their face. Not because of a political border, but because their bones might snap under the weight of our gravity. Is it ethical to create entire generations whose environment is a controlled experiment? Who are, from the moment of birth, subjects of a condition engineered by others? As we drift over the shadowed canyons of Valles Marineris, another pattern emerges in our thoughts, a memory from Earth. Settlements on new frontiers are rarely just about exploration. They are about economics. Whoever pays for Mars will expect something in return. History is full of colonies that began with promises of opportunity and ended with systems of exploitation. Company towns where workers bought food, water, and shelter from the very corporations that owned their labour. Contracts signed under conditions that made leaving almost impossible. Laws designed far away by people who never walked the streets they ruled. A city on Mars, cut off by distance and vacuum, would be dependent on whoever controls its supply chains, its air, its communications. The thin line between employer and government, between citizen and asset, could blur. If your oxygen, your water, your pressure doors all belong to a company, how free are you? Governance on Mars would start with idealistic charters and carefully worded agreements. But over decades, as repairs stack up, debts accumulate, and survival becomes a daily negotiation. The pressure to cut corners, to prioritize profit over people, may grow. In a world where a malfunction is a death sentence, dissent could be framed as a safety risk, protest as sabotage. We like to imagine Mars as a blank slate, yet our history suggests we would bring old patterns with us. Power imbalances, unequal access to resources, questions about who gets to decide the future of a place they do not personally inhabit but financially control. And behind all of this stands the grandest proposal of all: terraforming. The idea of reshaping Mars itself, giving it thicker air, warmer temperatures, perhaps even shallow seas, turning a cold desert into a second Earth. On the surface, this sounds like restoration, making Mars alive again. but we do not know what again truly means for this planet. The valleys that may once have held rivers, the minerals that hint at ancient lakes, they tell a story of climate and chemistry, not necessarily of forests and birds. Terraforming is not returning Mars to what it was. It is turning Mars into what we want. Ethically, that is a profound step. To warm the poles, to release trapped gases, to alter the sky and soil on a planetary scale, is to decide that a world, in its current form, is insufficient, that a pristine, ancient desert, sculpted by billions of years of dust storms and meteor impacts, is less valuable than an engineered environment fit for us. Some argue that planets are not sacred. They are raw material, and transforming them is simply what life does. Just as plants changed Earth's atmosphere long before humans appeared. Others respond that there is a difference between slow, blind evolution and deliberate, rapid redesign across an entire world. That perhaps some landscape should exist without our signature. While we weigh these cosmic choices, a more familiar question waits at home. Every dollar spent on launch systems, life support technology, radiation shielding, habitats, could it not be spent on Earth instead? On climate stabilization, on healthcare, on lifting people out of poverty, on restoring damaged ecosystems? When our own world is burning, is it ethical to build a refuge somewhere else? Supporters of Mars exploration counter that this is not a simple trade. The same technologies that keep humans alive in Martian dust storms can improve sustainable living on Earth. Closed-loop water systems, efficient energy storage, precision agriculture. In trying to survive on a dead world, we may learn how to better care for a living one. They also remind us that species which stay confined to a single planet are vulnerable. To asteroids, to supervolcanoes, to their own mistakes. Spreading out, they say, is not an act of abandonment, but an act of preservation, a form of cosmic insurance. And there is another, less practical argument. Expanding into space may deepen human consciousness. Standing on another world and looking up at a distant Earth could change how we see ourselves, our borders, our conflicts, our priorities. We may find new art, new philosophies, new ways of thinking born from a sky with 2 moons and no breathable air. As our imagined ship circles Mars one last time, the planet rolls slowly beneath us, half in light, half in shadow. The red plains glow softly. The polar caps glint with frozen water and carbon dioxide. It is beautiful and silent and indifferent. The ethical questions do not give us clear answers. They do not say go or stop. Instead, they ask us to move carefully. To admit that building a city here is not just an engineering challenge or a scientific mission. It is a moral experiment on a planetary stage. Whether Mars remains a silent desert, a scientific sanctuary, a struggling outpost, or a transformed world will depend on choices we have not yet made. For now, as the engines hum and we begin to pull away, we are left with a thought as thin and fragile as the Martian air. Perhaps the hardest part of going to Mars is not surviving there. It is deciding what kind of species we want to be when we arrive. Perhaps the problem is not the dream of Mars itself, but the version of the dream we have chosen. Not shining red megacities under domes, not highways of pressurized glass stretching to the horizon, but something quieter, smaller, and closer to the way we already explore the unknown. Before we imagine millions of people on Mars, we might begin with something that does not breathe at all. In the darkness between planets, the first pioneers are not human. They are machines. Robotic explorers do not fear radiation. They do not miss their families. They do not need air, water, or warmth, only power and a whisper of radio contact across the void. When we speak of impossibilities on Mars, we are speaking about human bodies, human minds, and human economies. But robots are not weighed down by these same limits. Think of the rovers already there: spirit, opportunity, curiosity, perseverance. Each of them was a single machine sent once, and yet together they have lived out something like a slow-motion colony. They have mapped valleys, drilled into rocks, tasted the dust, and watched the thin air change with the seasons. They have survived dust storms that would suffocate a human habitat in hours. A robotic presence on Mars could grow far beyond a handful of rovers. Imagine fleets of autonomous excavators chewing through regolith, swarms of small drones hopping across craters, towers of robotic greenhouses that never need a breath of oxygen. This is a kind of settlement that does not need to worry about bone loss, depression, or emergency surgery. It is a network of metal and code, patient and tireless. Such a robotic infrastructure could be our first true colony. A colony of instruments, a colony of tools that precedes us, preparing the ground. In this version of the future, humans do not arrive to build from nothing. They arrive to join something already in progress, landing near power grids assembled long before, moving into shelters carved out and sealed by machines, breathing air produced and stored by reactors that have been humming for decades. A city may be out of reach for now, but a robot-built outpost, maintained across generations of machines, is far closer to what our current technology can support. If we imagine people on Mars, perhaps we should begin not with a city, but with something far more familiar: a research station. On Earth, we already live on another planet, in miniature. It lies at the bottom of the world, locked in ice and silence. Antarctica. Humanity has not covered Antarctica in highways and suburbs. It has done something different. It has placed small pockets of life in an environment that does not want us there. Stations like McMurdo, Amundsen Scott, and Concordia sit on a frozen world of endless night and bitter wind. Supply ships and aircraft arrive on fragile schedules. Food is rationed. Waste is catalogued. Emergencies are handled within the limits of whoever is already there. An Antarctic station is not a city. It is a promise. We are willing to endure this place as guests. A Martian base, at least in the beginning, would likely resemble the Antarctica model far more than a science fiction metropolis. A few dozen people, then perhaps 100. Living in modular habitats, connected by airlocks and tunnels. Every litre of water tracked. Every tool inventoried. Every departure outside the habitat planned like a small expedition. There would be seasons of presence and seasons of absence. Crews rotating in and out. Long stretches with only machines watching over the base, waiting patiently for the next group of humans to arrive. In this way, Mars becomes less a second Earth and more an extreme field site. A place for focused research, not an endless sprawl. Something between a laboratory and a monastery, perched on the edge of another world. Before we reach even that point, there may be another step. Not on the surface of Mars, but above it. Orbit. In the emptiness surrounding a planet, problems change their shape. There is still radiation. There is still vacuum. But there is also freedom. An orbital habitat is not bound by dust storms, temperature swings, or the need to land and launch through a planet's thin, reluctant atmosphere. It can be positioned in stable orbits, adjusted over time, and expanded piece by piece. It becomes its own small world, turning slowly to create a hint of gravity, or floating weightless as an island of equipment and air. We already know this, in a smaller way. The International Space Station circles Earth every 90 minutes, a bright point drifting silently across our night sky. Inside, humans have lived continuously for more than 2 decades. They have performed surgery on equipment in microgravity, studied their own changing bodies, and learned how to laugh while floating upside down. An orbital station around Mars, or even in a gently balanced point between Mars and the Sun, could serve as a bridge. A place where crews rotate in, conduct operations through telepresence on the surface below, and then return home. Not yet settlers, but caretakers of the robotic colony on the ground. From such an outpost, round-trip times for signals would still be measured in minutes, but the delay would feel far shorter than the months it now takes for help to arrive from Earth. Robots on the surface would not be alone. Humans would watch over them, close enough to respond quickly, while still sheltered from the harshest demands of landing and ascent. Yet even this orbital future may itself be only a rehearsal. Another, closer stage waits in the sky above our own planet, the Moon. The Moon is not kinder than Mars. Its days are scorching. Its nights are brutally cold and last for 2 Earth weeks. Its surface is bathed in unfiltered radiation, and its dust is sharp and abrasive. But the Moon offers one gift that Mars cannot: proximity. 3 days. That is the distance, in time, between the Moon and Earth. Not 7 months, not a year. 3 days from accident to possible rescue. 3 days from sudden illness to an operating room at home. 3 days from starvation to resupply. If we accept that our first steps in off-world living will be fragile, then the Moon is the least unforgiving place to be fragile. It is a mirror where we can watch ourselves attempt to live in another gravity, with no air, no native water we can drink, and no environment that cares whether we survive. Lunar bases can test closed-loop life support, radiation shielding carved into regolith, underground habitats, and the psychology of small crews in isolated darkness. Every failure can be studied quickly, corrected and tried again. Every unexpected problem can be addressed without waiting half a year for parts to arrive. In this sense, the Moon is not a consolation prize for those who dream of Mars. It is the training ground that makes Mars even remotely plausible. When people speak of Mars cities in the 2030s or 2040s, they are whispering a wish into the wind. Physics, biology, and economics rarely move that fast. Technologies ripple outward slowly, like waves from a stone dropped into a lake. The timescale that truly fits the challenge may not be decades, but centuries. Centuries to build reliable fusion or advanced nuclear systems that can power a world without sunlight. Centuries to fully understand how to repair bones and muscles and minds that have lived most of their lives in low gravity. Centuries to evolve not just rockets and robotics, but laws, ethics, and shared values about what it means to spread life beyond Earth. This longer view may feel distant, but there is a quiet comfort in it. We do not have to solve Mars in a single human lifetime. We can add our chapter to a story that will be finished by others. Human ingenuity has never been a straight line. The solutions that will make any true Martian settlement possible may not resemble the ideas we debate today. Just as ancient sailors could not imagine GPS satellites, or early rocketeers could not foresee reusable boosters landing themselves on columns of flame, we are blind to many of the tools our descendants will consider obvious. Perhaps new materials will allow radiation shields as light as cloth. Perhaps biological engineering will let our bodies adapt in ways that no exercise regimen ever could. Perhaps consciousness itself will find new ways to travel, through telepresence, through uploaded minds, through forms we have not yet dared to describe. For now, the path that seems to respect both science and imagination is modest and patient. Robots first, then small, rotating crews on the Moon, then limited, research-focused stations on Mars, supplied by a network of machines already working the soil, orbiting habitats acting as guardians in the sky. Generations of gradual learning instead of a single dramatic leap. In that slower unfolding, the dream of Mars does not die, it deepens. It stretches itself across time, accepting that some destinations are not reached by sprinting, but by walking, step by careful step, across the centuries. We have wandered through deserts of radiation, seas of thin air, and the quiet echo of medical emergencies unfolding with no help on the way. We have traced the fragile lines of human psychology stretched across millions of miles, and followed supply chains so long that they begin to look less like logistics and more like lifelines. Piece by piece, the dream of a city on Mars has revealed itself not as a simple next step, but as a cliff edge at the border of what our current science, technology, and biology can truly sustain. But this is not a story meant to extinguish hope. It is a story meant to show just how vast that hope really is. When we say that building a city on Mars will never work, what we often mean, quietly, between the lines, is that it will not work the way it is usually shown to us. Not as a glossy colony under crystal domes, springing up in a decade or two, populated by settlers who adapt with little more than smart suits and good intentions. The physics of radiation, the frailty of human bones in low gravity, the unyielding chemistry of a CO2 atmosphere 50 times thinner than Earth's. These are not obstacles that yield to optimism alone. Never might be too strong a word for a universe that has surprised us at every turn, but not in our lifetimes, and not in the way it's being advertised, may be closer to the quiet truth written into the equations. Yet there is a strange comfort in that. To see the real scale of the challenge is to recognize the real scale of our ambition. Cities on Mars are not weekend projects. They are civilizational projects. They ask for breakthroughs in biology, medicine, propulsion, materials science, psychology, and ethics all at once. They ask us to reimagine what it means to be human far from home. In that sense, the dream itself becomes a kind of gravity assist. Just as Jupiter's pull can fling a small spacecraft toward the outer darkness, the idea of a Martian city can sling our curiosity toward discoveries we might never have made otherwise. Artificial gravity habitats spinning gently in orbit, radiation shields grown from living materials, closed-loop life support systems perfected first to protect vulnerable people on Earth. Each small step, grounded in realism, can still be guided by a dream that looks beyond the horizon. The danger is not in dreaming too big. It is in dreaming without looking closely. Honest scientific communication is not an enemy of imagination. It is its foundation. When we talk about Mars colonization as if it were just a matter of budget and bravery, we flatten a rich, complex tapestry of unknowns into a simple, marketable slogan. When we instead acknowledge the full depth of the problems, the brittle bones, the silent storms of radiation, the fragile human mind trying to stay whole in the endless night, we do something more profound. We treat our own future with respect. You are free to hold on to the vision of sunsets over Martian canyons, of lights glimmering softly beneath transparent domes. But perhaps, after this journey, that vision now comes with new layers, rotating habitats above Mars instead of cities upon it, robotic caretakers preparing the ground, human visits measured in careful months instead of generations, and the acceptance that some places may be better visited than permanently inhabited, at least for a very long time. As you drift towards sleep, you are invited to keep both things in mind at once, the wonder and the questions. Let claims of easy colonization pass in front of you like distant stars, and examine them gently. Who pays? Who suffers? Who benefits? Which parts are engineering, and which parts are wishful thinking? You don't need to reject the dream. You only need to see it clearly. Thank you for traveling through this quieter side of the Mars conversation, through the science that so often lives in the footnotes rather than the headlines. Your curiosity is what brings these distant worlds and these difficult questions into focus. If you'd like to help this journey continue, you can softly tap the like button or subscribe so you don't miss our next voyage through the cosmos. In the comments, you're invited to share where you're listening from, what city, what country, perhaps even what time of night. It's a reminder that, for now, our first and only true home is this one small world we share. For those who wish to support the channel a little more, there is also the option to join as a YouTube member. It's never expected, always appreciated, and it helps us keep crafting these long, quiet explorations for you. For now, let the questions settle like dust on a distant plain. Mars will still be there in the morning. The universe is in no hurry, and neither tonight are you.